right. Let's get started for today. Let's see, where are we in the class? We covered a lot already. We covered thus far all generative models, though. Models that are built in a way that you can sample from them to generate new data similar to your training data. And often that might be what you want, but often what you want is actually a model that is just a pre-trained model that you can then fine-tune for a task you care about. And really what you want from that pre-trained model is that it somehow extracts good representations from your data. The generative models can do that too, but you could say, why not just purely focus on getting good representations? Historically, the way people got good representations was by training supervised. And that was one of the big things in deep learning that never happened before in other types of learning. You do supervised learning, deep learning on ImageNet, and it turns out the features that you get from supervised learning on ImageNet also do well on other data sets. So that was the initial version of kind of pre-trained supervised on ImageNet. But that didn't scale because then people need to annotate too much data. And so today we're going to look at self-supervised learning approaches, which means looking at approaches that try to really focus on the pre-training and get good representations out. And so almost all the evaluations we'll see today for the papers that we cover will be along the lines of, after we pre-train, we now fine-tune or put a linear classifier on top of the learned neural network and see how well it does with a small amount of data or modest amount of data, very often, but sometimes also with large amount of data later used, and see how well it does compared to training from scratch. I'll cover roughly the first half. As I had mentioned on Ed, but I want to also say it in lecture, unfortunately I can't do office hours today. I need to go to a Berkeley fundraising event, support our chancellor, meeting some donors, go home, put on a suit, and like show up there. And talk about AI. So, I mean, it should be a fun one, but it won't be nearly as detailed AI chats as we have here, but I'll still be talking about AI. So I won't have my office hour after lecture. I'll probably even take off midway through, right when Philipp takes over. But as I said on Ed, if you wanted to catch me today after lecture and you really want to catch me soon, drop me an email, and we'll find the time to set a video call. Probably would be on either Friday afternoon, so tomorrow afternoon, or on Monday, we would do a video call. Okay, so this is an example we're borrowing from Ian Goodfellow, the inventor of GANs, from one of his tutorials. And essentially, the point is that good representations matter. If you want to learn a classifier between the blue circles and the green triangles, it's much easier on the right, where they're already nicely separated. Just draw a line between them. Whereas on the left, you have to find essentially a circle between them, which is a more complex thing to learn and to position correctly. What's the difference? X, Y coordinates versus polar coordinates. Now, this is a hand design example, but it's to showcase the notion that if you can somehow come up with the right representation, either yourself or through learning, it can help you solve a problem more easily afterwards. In deep learning, the way this tends to work is that in goes pixel level things. If you just process pixels, raw pixels with a modest amount of processing, you're not getting a whole lot of information out of it. What we see in these networks is that layer by layer, and this started with supervised learning, where we already saw this, but now today we'll cover self-supervised learning. Early on, there might be edge detectors, then there might be circle and other shape detectors, and at some point there might be face detectors and so forth that emerge inside these networks. And so essentially what's happening is like small little units initially get composed into then bigger and bigger units that are being recognized in some more semantically meaningful way inside the network. And again, if you had a network that was pre-trained and already had a neuron for, I don't know, face, or for smiling face versus sad face, eyes closed, eyes open, all that stuff was already in there. Training something on top of that to then recognize whether somebody is happy or sad becomes very, very easy to do. And so keep that in mind, that's the common thread for today's lecture. So the goal in representation learning is to pre-train a neural net. Connection is, make sure I didn't plug poorly. The goal is to pre-train a neural network so it can be fine-tuned to have good performance on a downstream task with limited downstream data. Generative models, they can achieve this, but today we're going to look at alternatives which do not involve a generative model. Okay? We were chatting before a lecture here, and somebody brought up over 300 slides today. Yeah, it's an amazing set of slides, lots of slides. One of the crazy things about self-supervised learning, and thanks Philipp for contributing your fair share. Amazing about self-supervised learning is that there's just so many different ideas. The other thing that's a little funny about it is that the ideas tend to be very pragmatic and conceptual. There don't tend to be a whole lot of mathematical derivations involved. With the VAE, there's a lot of derivation to get what we needed to get. With a GAN, once you start thinking about it, there's a lot of math too. With these self-supervised methods, it's almost like a massive bag of tricks combined with good deep learning expertise, and all of a sudden you can get amazing results, and sometimes better than other times. As you'll see, the master of all tricks, Kai-Ming He, has written some of the most important papers we'll cover today. He just gets things working other people didn't know could work, which is very interesting. And I think it's a pretty unique thing about self-supervised learning. We'll see in the beginning of the lecture some things that people tried, it didn't work, and then 5 years later, Kai-Ming redid it, and it worked, and it's state of the art. So, interesting things ahead here. A version of unsupervised learning where data provides the supervision. In general, we withhold some part of the data, and the task a neural network is tasked with is to predict the data we withheld. So some data, pull some out, neural net, fill it back in. That's the big picture for all of today, pretty much. But choosing the right kind of task, the right kind of data or angle of data to slice out is really what makes all the difference. I want to give a little extra motivation. This is from a keynote Jan LeCun gave at NeurIPS, I believe in December 2015 or December 2016. So quite a few years ago. At the time, all the excitement was reinforcement learning. I'm still a big fan of reinforcement learning, but back then everybody's excited about reinforcement learning because DeepMind's breakthroughs with AlphaGo, the Atari games, at Berkeley we had the robotic learning breakthroughs, and so everybody's excited about deep reinforcement learning, and Jan wanted to give people a reality check. It's not all about reinforcement learning. He said, you need data. Most of your data is going to be unsupervised or self-supervised. That's the foundation of the cake. That's the big data. Then you might label a little bit. That is now known as the supervised fine-tuning stage of ChatGPT. He essentially predicted the ChatGPT sequence of training. And then the final step is essentially the RLHF or the RL, which is the cherry on the cake where you have the smallest amount of data. It's important to make things work the way you want them to work, but it's really the tiny thing that happens all the way at the end. So I think pretty interesting that essentially ChatGPT, the way it was trained, completely predicted 6-7 years before that by Jan LeCun with his cake. Well, the foundation of the cake is what we're focused on today. And there's a lot to cover. Let's just dive in, I guess. So, even before deep learning was truly successful, actually, there was already work on self-supervised learning. Yes, question?
Very small question. Like you mentioned, the self-supervised learning part of it will affect text models that trained like in an autoregressive way, and we studied autoregressive models. So, what's the difference between unsupervised and self-supervised?
What's the difference between unsupervised and self-supervised learning? I would say unsupervised learning is any kind of learning where you don't do any explicit effort for data annotation. You might still write a download script to download a bunch of data, but you're not sitting there adjusting labels or anything like that. That's unsupervised learning. Now, within unsupervised learning, I would argue there is two categories. One category is generative models, and the other category is self-supervised learning. Generative models, you can use the model that you train to regenerate data like your training data. Self-supervised learning, typically that's not the intent or possible. And so it's a different category of models that we'll cover today, but that's how I would essentially sketch out the landscape. Turns out people were doing self-supervised learning even before deep learning worked. So deep learning only started working in 2012 with AlexNet breakthrough. Even before that, people were doing self-supervised learning. In fact, people didn't know how to make deep learning work. And for the longest time, people thought that maybe the only way to get it to work is by doing self-supervised learning and then fine-tuning afterwards. That's what people were trying at the time. And it was in some sense to many people a surprise when AlexNet came out that it was fully supervised. There was no pre-training, nothing. Just fully supervised, got the job done. Big surprise at the time. To most people, at least. I'm sure not to Jeff, but to most people. So in a denoising autoencoder, you have an image in this case, you add noise to it, that's number 2, but with a bunch of noise, you encode that image, you then decode it, and hopefully you get back out the original image. Might remind you of diffusion models, put noise on it, try to denoise it. In fact, when you look at the picture this way, it's essentially the same thing, but bear with me as we go through this. So, the way this was done back in 2010, because deep learning was actually very hard to do, gradients wouldn't propagate through the network back then. The tricks didn't exist to get the gradients to propagate, so things were trained one layer at a time. So you have your image, you encode with one layer, you decode with one layer, and you hope you recover a denoised version. After you do that for a while, you've trained your first layer of your encoder and your last layer of your decoder, and then you start doing this again and again. So, what kind of noise? Could be Gaussian noise, could be masking noise, could be salt and pepper noise, which means saturate to bottom or top level of activation. That's possible. So people try all these kinds of things. Might remind you of many things happening today, but this is back in 2010. The way to think of this is that as you put noise on your data, you're essentially pushing your data off the manifold, and what the denoising autoencoder is learning is to get you back onto the manifold. This is what it would look like. Essentially, you have some kind of loss where you try to have your reconstruction be as close as possible to your original. Well, let's not get into details. Details have all changed dramatically since then. Then you repeatedly stack that and can get a deep network that's trained iteratively layer by layer to then have a representation that might take multiple layers to compute. Then at the end, you add on a supervised cost, or typically called loss these days, and you train for what you care about, let's say classification or segmentation or something else. Of course, it might remind you of diffusion models, which effectively are doing the same thing, conceptually at least the same thing. The details have changed, but you put noise on your data and you learn to denoise it. Diffusion models are generative models in that we can start from a completely noisy image and turn it into image that looks like a real image. But same thing with diffusion models. You could pre-train, and then you could later fine-tune or even zero-shot annotate for segmentation. So think of diffusion models maybe as the modern incarnation of these denoising autoencoders. How about instead of putting noise on it, you mask things out? This work started here in Berkeley, 2016. Predict the missing pieces. The idea being, if a neural network, and at this time people had figured out how to train deeper networks, so you could in one go train a deep network to solve a more complicated task. Let's train it to fill in the blank. Now, it's not a deterministic task, but you have supervision and you train a network to try to match what's in your supervision while also having some generalization capabilities. So the network takes in the image with masked out region. There's an encoder, then there's a decoder that fills back in the blank, and you have a loss that compares the two. There's different choices you can make in terms of what to blank out. A big region in the middle, smaller regions spread out, or maybe you kind of run maybe some kind of segment or something else that you have and just segment out a whole segment and see if it can learn to fill that back in. One of the things that they notice is that it's important to use both a reconstruction loss and an adversarial loss. When you just use reconstruction loss, as you'll see on, well, it's not there yet, as you'll see on one of the next slides, you fill in with something very smoothed out, doesn't look very real, it doesn't learn enough. If you include an adversarial loss, like in GANs, you get a much more interesting fill-in-the-blank behavior. And the notation here is essentially just saying that the loss is only defined on the regions of the image where you had a blank. There's no loss on other parts of the image. You don't worry about what the network is doing there. Now, you could debate that. You could say maybe the adversarial loss should be on the, in some sense, acting on the entire image, because if you fill in a blank and it looks realistic, but it doesn't match well with what's outside the blank, then what are you doing? You didn't really get it right. But in their work, they chose to have the adversarial loss focused on just the blank, and the reconstruction loss hopefully helps ensure that it's filled in a compatible way rather than just in a realistic way. So here's what their architecture looked like, the kind of networks that were used back then. You could probably, Kai-Ming He revisited this. We'll talk about that with more modern architectures. But this is what was kind of the first incarnation of this. If you just use the L2 loss, you get this fuzzy fill-in in the second image. If you just use the adversarial loss, you get a very realistic fill-in for the blank, but it doesn't really pay attention to anything else, but it looks realistic for the blank. If you use the joint loss for training and then fill back in, you get something much closer to what you want. Then there was a comparison here. So you pre-train, fill in the blank. I believe they did this on ImageNet, which was a larger data set. And then they look at classification on ImageNet, which is the large data set at the time. And then they look at detection and segmentation on a different data set called Pascal, which is a much smaller data set. And so what you see here is the effect of ImageNet pre-training helping detection and segmentation on Pascal. And you can see that the hours, so the fill in the blank, is pretty competitive with the other self-supervised methods. Not all the way at the top, but quite competitive. Same for detection. And same for segmentation, where it's actually best. Supervised pre-training on ImageNet was still better. And in fact, that's a trend. You'll see that only once people start training on very large data sets, much larger than the ImageNet data set, you train more, larger scale, you start getting real benefits from self-supervised learning. Okay. So the whole point is you predict one view from another. You go from raw data to corrupted raw data, denoising autoencoder, and try to recover the original. You could do this across channels. So what if you had multiple channels, let's say RGB? Maybe you can blank out some channels instead of a region and try to reconstruct the other channels. This is also in Alyosha's group actually here at Berkeley. They were doing a lot of the early work in this space. The original image is a color image. It's translated in a space, not RGB, but LAB. L is essentially like the grayscale image, and then AB are the color aspects of the image. If you combine them together, you get back the original image. Just a different space compared to RGB. And so they said, what if we set it up? We convert all our images to LAB space, give the network as input the L channel, and ask it to predict the A and B channel. That's a well-defined prediction problem, and all color images on the internet, you can just download and train on them. So it's a very nice way to do things. Of course, if your final classification task cares about color, you might be a little bit out of luck because you don't get as much information about color the way you learn in your self-supervised learning. But you actually implicitly learn a lot about color because you learn to fill it in, and you learn a lot about the structure of what's in the image to do that well. And so here's what it can do. Fill things back in. Then one thing they looked at is, okay, what loss should we use? Back then, it wasn't yet so common to avoid the L2 loss. So the L2 loss on reconstruction tends to give those averaged results. You can't model a multimodal distribution. So if your training examples are such that really there's a multimodal prediction that might be needed to cover the distribution of outcomes, L2 is a bad fit. And with coloring, actually, it's often the case that there's multiple possible colors. The car could be blue or green or maybe red and so forth. And that's not always so easy to see from the grayscale image what color a car or a bird really is. So you get something in between. Brownish birds come out all the time. But if you do pixel-wise classification, meaning as you color back in, it's a logit with 256 values for each channel. Then you can model multimodal distributions, meaning that then when you sample, you can also get one of the peaks of that multimodal distribution sampled rather than being somewhere averaging between possibilities. So they did this. That was one of the main observations from the paper, using the cross entropy discrete loss effectively rather than the L2 loss makes a pretty big difference. And then they augmented this with another version of this where they said, oh, what if we, instead of splitting into L and AB, and L is the input and AB is the output, what if instead we split into L and AB, and then we have two networks process it, and they each have to recover the thing that they don't have, and then we add them together, and the final loss is on how well it reconstructs the original image in some sense. And that's called split brain autoencoder. And here's what you get in, a pass through this kind of network. F1 and F2 are the trained networks here to recover the opposite channels, and then combined you get the predicted image back. Obviously you got to be a little bit careful, because the simplest solution, if all you do is doing addition at the end, is to just pass everything through, not try to predict the opposite. There must be an additional loss there to prevent that from happening. You can use with other things. Here they did it with depth channels and RGB. So you have a RGB-D camera, collect data from that, and then try to do cross-modal prediction. Now, one of the things that I thought was pretty intriguing then, different groups, instrument groups, showed that if you do color prediction, even though it might be hard, maybe in video you can frame the problem slightly differently. You can say, hey, instead of predicting color from nothing, I'm going to give myself access to the very first frame of the video. And then I get grayscale, and I'm supposed to predict the color in all the future frames. Now you have a much better posed problem. We know that multimodal distributions are much harder to train for than unimodal. You get much closer to unimodal distribution in this case. Because really what you're doing is you have to look up in the first frame for everything you see in a later frame what it corresponds to. And so it's a way to phrase a correspondence learning problem effectively. And it actually works really, really well. Look at this car coming through. So obviously the car is not all green, but the way this is highlighted is same for the birds. They don't have that color, the people, but it's to highlight a segmentation. You segment in the first frame what you want to track, and then it shows how it tracks it throughout the video. So you get some really good learning to track objects. Now, the paper that probably had the most influence in the vision space, at least in self-supervised learning, is the MAE paper, Masked Autoencoders. Interestingly, along the same line of work, but just some details maybe were gotten a bit more right. It was more the right time maybe to try it. In the masked autoencoder, the input is an image. A bunch of regions are masked out. Then an encoder encodes the non-masked out regions, patches, and then from that you get an embedding. And then a decoder puts blanks for the missing pieces, and then starts decoding onto, hopefully back to the original image. You see what I put there? Big, encoder big, decoder small. That's a design choice. The reason it's chosen that way is, well, you want an encoder that can capture the richness of what's in images to get interesting semantic representations. So the encoder is actually what we care about here. We don't care about the decoder. You kind of throw that away afterwards. The encoder is the thing you care about in this training. So let's spend our compute there. The other thing that's happening here is that the encoder only has to process a small fraction of the patches. The kind of hyperparameter setting that tends to be popular is only 25% of the patches remain, 75% of the patches are masked out. Okay, so the encoder only has to process a quarter of the amount of data that comes in compared to the decoder. Another thing that's interesting here is that if you want to process a patched up image effectively, traditionally images are done with convnets. It's pretty complicated if convnets somehow deal with these patched up images where some pieces are missing and so forth, let alone really throwing out 75%, not even doing any calculation for those locations. So this also coincided with transformers becoming much more popular in computer vision. The architecture uses a vision transformer, and so a transformer has a very easy time essentially just, however many patches come through, it has no problem dealing with that. Every patch has a position encoding, so the transformer knows where it came from, but it's okay if some are missing. It just won't have any queries going out to those missing patches. So just saved computation. Another thing that's worth noting is in this case, the patches are just with a linear projection fed into the transformer architecture. That's pretty simple, and I think it's a very natural choice because you're trying to do representation learning. If anything you put there before you're essentially forcing some other representation learning, or you have a pre-trained thing you put in there. So it makes it maximally flexible for the encoder to learn the representation rather than you forcing anything onto it. So it's pretty interesting what it looks like though, right? When 75% is masked out, look at the top left, for example, that's a clock. But for a human, it's pretty hard to see that that's a clock. But the MAE, after enough training, can recover the blanked out patches and show that's indeed a clock. Same for all of those. And by the way, the 75% masking was a very high masking ratio. I don't think anybody expected that to be the right amount of masking until it was shown to be the thing to do. Look at the earlier paper we covered, just block out some region in the middle or some region a little somewhere else. It was nowhere near 75%. And the counterpart in language, BERT, which had been around for a while, masks out about 25-30%. So the natural thing to try and envision would be to also do 25-30%. Maybe people tried it, got not that great results, never got published. But in this paper, they decided 75% might be what's needed, and indeed it does very well when you mask out enough. The intuition people have for this is that if you don't mask out enough, the task might be too simple, and so you can just copy things over from patches that are not masked into the masked patches, and you're not really learning a representation that's truly semantic. This is on validation images. You see, so again, the reconstructions are in the middle. It's quite good. Here's a study of the masking ratio. If later you do fine tuning or later you do linear probing, in both cases it seems like a masking ratio around 75% is quite good. Though for fine tuning, I guess you have more flexibility. Because I guess you get to train more later, whereas with linear probing, you need to learn your entire representation during the self-supervised learning, so you need to get the self-supervised learning to be done better. Is there a question somewhere? Yes?
The architecture looks very simple, like again, so what is making it work with people would not have done before this?
Yeah, how come something this simple could be so much better than what was there before? Sometimes people just overlook the right things and sometimes the right time to do something, and it's a combination of both. So this came right after the vision transformer came out, which was the first paper showing that transformer architectures, if you have large enough training data, they might need a bit more training, but if you have a large enough training set, they can do as well as ConvNets. Okay? Now, there's two aspects to that. One, transformers are very flexible, so it might help to use a transformer architecture here. But until then, it was not necessarily expected, envisioned that would work. It seemed like ConvNets was such a great prior, locality, and so forth. And so trying this with ConvNets in the past hadn't worked out all that well. The other thing is when you try with a ConvNet, it's actually very hard to make this work, because what does it mean to mask something out? You're putting blanks there, but your convolutions still run over it. And so you're still processing those regions. You're just processing zeros there, and so it's you kind of get an out of distribution behavior. Whereas with a transformer, you don't get the out of distribution behavior. You just have as many others that you can do a query to, and that's it. And it gets normalized, your inputs, and everything just works out. It doesn't matter how big or small your images or how many patches. Whereas with ConvNet, where you mask, how you mask, all that stuff will influence later in the fine tuning when you're not masking what happens now. So there's like a mismatch, a fundamental mismatch to fine-tuning. And I think people also just never thought of this big a masking ratio being the thing to do. It was very surprising that that's how much you have to mask. And sometimes that's part of it. The devil's in the details. It's possible somebody tried a vision transformer, tried all the same things, but didn't mask as much. And the masking gives the right inductive bias to learn semantics, but also allows you to scale up the training. Because you mask out 75%, you can effectively train something four times bigger, because you only need to do 1/4 of the work for each data point that you get in. And so you can train a bigger encoder or train more data, 4 times more than somebody who doesn't mask much. So yeah, it's interesting how these things play out. I would say at the time, to give a bit more context, and Philipp will talk about that line of work, the bets people were making, or the most commonly used approaches to self-supervised learning in computer vision, were not based on masking. they were based on something called contrastive learning. Very different line of work, and there was a lot of progress in that line of work. Has many interesting ideas that still are quite relevant, but to some extent people had stopped trying to straight up mask things out and fill a black in. Interestingly, Kaming also did one of the main papers on the contrastive learning front, so he covered both with his work. But I think actually sometimes that's how it is. You know, you work on something, you're at the frontier, and you start realizing maybe there's still something missing. And while everybody else is still excited about this line of work and thinks that's where they should go, you've already thought that actually there's the next thing that you should be moving to. And that's ideal if that's what you can do. So, comparison with prior state of the art, consistently beating it. We'll cover some of these works. None of these have this kind of format that of fill in the blank. So it's pretty. Actually, BEIT does, but it was like in some sense, like an attempt at MAE that got a few details wrong and hence didn't work as well. But it happened before, and it was a step in the right direction in some sense. So there are many MAE cousins and derivatives. Most of these are derivatives, and that's also acknowledged in the name. They all have the MAE or AE at the end of their name, and giving credit to the MAE paper. BEIT actually happened before MAE, but I didn't cover it before because MAE is the most important one today. But now I'll also tell you what BEIT did. So this was saying, why don't we just do BERT pre-training of image transformers? So also transformers, also fill in the blank. What did they do different? So they pre-trained a tokenizer, and then effectively the masking in the tokenization space, which means that you don't learn part of it in this process. Part of it has been pre-trained with a discrete VAE, which might be something you want or don't want, but you kind of don't have access to that. That's pre-trained. The other thing that happened in their setup is that they didn't mask out as much. And so that's another setting they did differently. And they did not remove the masked out patches. They also processed the masked out patches. So those are some differences between the two papers. And again, to your question, where did it come from? How did it work now? It's these details. I mean, BEIT is essentially as close as it gets to MAE without getting there, at least in the history of how things were developed. Video MAE builds directly on MAE and says, okay, well, why not do the same thing for video? Couple of things to think about. They call out this notion of tube masking. What is tube masking? It means that usually when you have a video, if in a certain region of the frame, there is something now, it might also be there in the next frame. So you should mask out where in a specific region you mask out everything or maybe nothing. Because if you sometimes mask out this location and that location, you can just copy from the previous frame to the next frame to fill in that region, and the task becomes too easy. So that's what they call tube masking. Make sure you can't do simple copies from frame 1 to frame 2 and so forth. Otherwise, essentially MAE, high masking ratio, even higher than MAE, 90 to 95%. Why? Because video is even more redundant than images. So you need to mask out even more to prevent the task from becoming too simple. Very impressive results, even on very small data sets. This is the pre-training actually. Even when they pre-train a relatively small data set, 3,000 videos, they get good representation learning. One of their observations was that data quality is more important than data quantity for this pre-training. And domain shift between pre-training and target data sets is an important factor. So video MAE with a vanilla VIT vision transformer backbone can achieve 87.4% on Kinetics 400. These numbers in the abstract maybe don't make that much sense to you, but essentially these are good performances on these data sets. And if you're looking into video generation or things related to video, these are data sets you might want to look at. Kinetics 400, something V2, UCF of 101, and HMDB 51. They're good ones to look up if you're working in this space or plan to work here. Yes?
What is meant by data quality here?
So I think what they meant is that they want higher quality videos. I don't know what else they tried. I don't recall what kind of other data sets they might have tried where the quality wasn't as good. That's a good question. We'd have to go look back at the paper. So here are their results for different sizes of vision transformers, and turns out that on these, benchmarks they're considering here, they tend to do very, very well, and they have to use no external data, whereas many of the other previous learning representations from video and then fine-tuning something else had additional pre-training on other data sets. Yes, question?
Like the diffusion models and the stuff you were showing from 2010 earlier, it's effectively like you noise all the data and then you're trying to extrapolate the original image from something that looks nothing like the image. And then here it's almost like interpolation. When you mask things out, you just want to fill in the blanks. But it seems like extrapolation is a better way to learn because they're almost masking everything out to learn. So it's like, is it better to remove as much of the initial information as possible? Because right now, like, diffusion models work the best from what I understand, and that basically removes everything through that iterative noising process. So is that why this extreme masking is better?
So the question is essentially, how extreme should the masking be and how much noise to add, and what are the trade-offs? Yeah. In these papers, the finding is that you need to mask out a lot. I think you essentially mask out as much as you can while the thing still can come up with some kind of solution to your problem. I think the challenge if you mask out too much is that the solution could become multimodal, and multimodal distribution modeling is harder. And so you probably want to mask out as much as possible while somehow having a unimodal distribution over what the fill-in should be. Now, what does that exactly mean in terms of amount of masking? I think you just do it by, doing a hyperparameter search. If you compare it to diffusion models, they can come all the way back from full noise onto real image, but if you go to full noise, they don't come back to the original image. Like we saw in the examples, when in the original diffusion paper, you could go 1,000 diffusion steps and you wouldn't recover the original image. You could go up to 500 and you could still recover the original image. And so now to us, that noised after 500 step image is pretty hard to still discern what's going on, but I guess to a computer it's still more clear because it's not as distracted by all the little noise spickles, is my hunch. But I would also, the other question you had is, are the diffusion models better than these? Diffusion models are the best for generation right now. I don't think they're necessarily always the best for representation learning. I think a lot of the representation learning today is still done with masked autoencoders for vision. Experiments on kinetics 400. So typically in these video data sets, essentially you need to recognize an activity. So kinetics 400 means that there's 400 different activities, and when you are doing the fine-tuning or the linear probing, you're asked to learn to predict what activity was happening in this particular video. So VME is very good. Here's another idea. Again, I think a lot of today's papers that we cover, the ideas are very clever, but then the math doesn't have to be that deep. That's why we can cover so many papers. But often in deep learning, that's the winning strategy. The more complex your math becomes, it's almost guaranteed that your experiment won't scale as well. And if it doesn't scale as well, then your results won't be as good. So it's good to keep things relatively simple. But you want to leverage some kind of intuition, right? Think back to the coloring, right? Where you got the first frame and then grayscale for the future frames, and you color back in by being able to refer to the first frame, and we got an automatic segmenter out of it, effectively a tracker. In the SIAM MAE architectures, that's essentially revisiting that exact same idea, but with the tools from 5 years later. Use a vision transformer, use the MAE idea, and the results get better. So here you have a video, you will get the initial frame, you'll patchify, encode, keep everything. You take a future frame, you mask almost everything out, and the task is to fill it back in. Now, in the video MAE, we didn't want to do that. We said we could just copy things over. It's too easy. We're not going to learn the right representations, but that depends on what you're trying to do. In video MAE, we're trying to learn semantic representations. Might this be a dog jumping or a dog maybe lying on the couch? That's different semantics. But here, the goal is to learn to track, to segment. And so it's a very different goal of what's being trained for. And when you want to learn to track, you want to learn to make correspondences with the previous image and understand where things ended up in the next image. And so the way to think of this, and that's how the authors explain it, I really like the explanation, is the few patches you get to see are essentially telling you how things moved, give you a global sense of how things moved, and now your neural network from that needs to be able to fill in where everything else is going to move to make it consistent. And being able to do that makes it able to do good tracking. 95% masking in that second frame. Outperforms state-of-the-art self-supervised methods on video object segmentation, key point propagation, and semantic part propagation. So these are all segmentation, propagation tasks, different from the video MAE, which is about classification. So here's what this looks like, but actually there's some really cool videos that I want to show this in action. So here's what comes out of it in terms of the ability to track. So you essentially annotate in the first frame what you want to track, and then, or who you want to track, and then from there, it just automatically tracks that throughout the video. Here's another one where you're supposed to track essentially the skeleton that explains the pose of the person. And again, it's able to learn to do that state-of-the-art performance thanks to this kind of pre-training. And then there should be one more. This one here is parts tracking. So is a person, you actually split up in, let's say, hair, face, t-shirt, and so forth. And it can track the components or the parts of that person throughout. Yes, question?
So when you say that you annotate the first image, do you just literally paint parts of it different colors?
I don't know what they did here. That's a good question. How did they annotate the first image? I could see this happen in two ways. One is if you care about something specific yourself, probably what you do is you run a standard segmenter on your image, and then you click on the regions that you say, these are the regions that constitute the object I care about. Maybe it already has that as a separate object, maybe not. Maybe you need to merge some or split something. Or you could, in principle, just segment the initial scene automatically and then just let it track all segments over time. That's not what they did here. Maybe because that's hard to see what's going on, because there might be a lot of little segments doing things that are hard to make sense of. And so in the examples here, they focused on the main subjects in the video. And yeah, I don't know if they manually chose the segments or whether they had some kind of other system to grab the person and then track. Either way is reasonable.
And as far as producing all these future frames, do they essentially take the first frame and then take the next frame, which is not segmented, and then mask it out and predict it with the decoder? That's
a good question. I should look up the details again to answer that question, but I think there are two options here. Oh, you remember?
Yeah. They essentially they encode the first frame, extract out those features, and then they condition on that frame and then use the encoder to extract out corresponding features, and they try to match the features with the original frame. So they just, for each frame by frame, they're just doing a pairwise matching, and then they project that back into the corresponding feature space.
Thank you, Philip. Yes, question?
So you have say you have a scenario where instead of a video you have several images taken about the same instance back to back. Would it be able to work, or because the number of images cannot come close to this in terms of available frame, you can't do the same thing?
You mean in terms of training?
Yes.
So yeah, I mean, to train this, you do the assumption here to train this is that you have video that is meaningful in a consecutive sense. If you had cuts in the middle of your video, you want to essentially curate your data set, that when there's a cut and you go to a different scene, that becomes a separate part of your a new item in your training set. You don't want transitions across those because you're not going to be able to color things in, or in this case, I guess, fill in the blank across those cuts all that easily. But it all depends. Maybe for some cuts you can still do it. But if it's a cut to a completely different scene, then you probably stand no chance. So in some sense, yes. I mean, it's worth, I guess, highlighting that even though we call it self-supervised and unsupervised learning, there is a certain amount of data curation still happening. Now, some of it can be scripted. You might say, hey, if my next frame is this much different from the previous frame, I assume there was a cut, and I'm going to split it up. So there are ways to maybe script it, but there is some kind of work involved making sure that your training data is well behaved with respect to the assumptions you make here for the training. This is kind of just highlighting the state-of-the-art performance attained on these tracking tasks. So I guess this is video object segmentation, human pose propagation, and semantic part propagation. And this work is state-of-the-art across all of them. Turns out you can do the same thing in a different modality, audio. You encode your audio into a spectrogram, which means essentially you take windows in time and take the Fourier transform over that window and look at the data in the frequency domain for that interval. Feeding only the non-masked tokens through encoder layer, so just like MAE. Decoder, same as MAE, you reorder to make sure things are in the right spot, fill in the blanks. Local window attention in the decoder, this is a little different. They had a decoder that's a bit more attuned to audio data, where apparently there is a lot more locality that matters. And so a little extra work on the decoder there. Fine-tune the encoder with a lower masking ratio on target data sets. That might be to get more in distribution for when you do your downstream tasks. And then apparently sets new state-of-the-art performance on 6 audio and speech classification tasks, outperforming other recent models that use external supervised pre-training. So after the MAE paper came out, it's just like this sequence of works that came out that established new state-of-the-arts in self-supervised pre-training or even any kind of pre-training. This is the architecture. You turn your audio signal into the spectrogram. You remove most patches, do an encoder, decoder, and that's essentially MAE. It looks like MAE pretty much because the spectrogram looks like an image. These are some of the numbers they achieved. I'm not an expert in audio, so it's hard for me to give a lot of detailed comment on these numbers, but I think the important takeaway here is that it's achieving state-of-the-art. And the beauty of MAE is, of course, that it's one of the simplest ideas. It's just fill in the blank. So it's nice to see the simplest thing do so well. Multi-MAE. So what they did here is they said, why just, one modality? Why not multiple modalities? And you can have different kind of mask out ratios for different modalities, different combinations of ratios, and then you can learn to fill in other modalities. Maybe you have RGB as always, then you have depth, maybe you have semantics. They use semantic segmentation as one of their input channels, which doesn't really feel like all that self-supervised, but their take was essentially there's a lot of pretty decent segmentation algorithms. Run those, combine it with this. It's not being trained to do segmentation, it's trained to do representation learning. And so having also the segmentation as part of the training effectively makes it work harder. To also figure out some of those things, and it helps in their experiments. And then at test time, you can in principle then use it as a segmenter. Of course, the segmenter will only be as good as your pre-labeled segmentation data, but your representation learning might be very good, and then you can fine-tune on more segmentation data if you want. Encoder only processes the non-masked tokens. That's the common theme. Shallow decoders, pseudo-labels for the non-RGB modalities. Evaluations on ImageNet 1K. I don't really know the other data sets as well. Semantic segmentation data sets, and apparently doing quite well. More experiments here. So These are cross-modal predictions, RGB input into depth prediction into semantic prediction. You go from depth to the other two or semantic to the other two. So in some sense, it's a bit of a generative model in this case because it can reconstruct other modalities from the original input. This is work we did at Berkeley. At the time, there wasn't really anything yet. This is now a year and a half ago. Anything yet that was particularly good at multimodal learning between text and images. There was the clip-like learning, which was the essentially contrastive learning Philipp will cover. But there wasn't something MAE style that might actually be better. So the dominant multimodal representation learning paradigm at the time was contrastive learning. Downside of cross-modal contrastive is that it only works with paired data. All your data has to be paired, otherwise it doesn't really contribute to the training. This case, we found out multimodal pre-training of M3AE on this closed captioning dataset achieves significantly higher performance on the ImageNet 1K linear classification benchmark compared to pre-training on images only. So there's something about the multimodal that's helping extract a better representation of images. Not too unexpected, because obviously having that semantic information should tell you something about the images. That is not just there if you do just image training, but it's nice to see it confirmed. Performs best when apply a high mask ratio even on language, which was a bit surprising at the time. At the time on language, everybody used like 30% BERT-like masking. In this case, 75% seemed to be a better choice, maybe because there is a complementary information in the images. In fact, sometimes even lower than 30% on the BERT models. Encoder, image patches and language tokens, vision transformer, decoder, also very lightweight, following all the MAE, learned lessons. You feed in image, patchify it, only feed in the patches that are not masked out. You feed in the text, you also blank things out there. Your encoder does then a lot of the work, and the decoder is supposed to reconstruct the pair, or sometimes just the image, just the text, if that's all you have. Comparison, just a second. Comparison with MAE. On fine-tuning accuracy, it's strictly better than just MAE. This is a pure vision task. Linear accuracy, it's a lot better, showing that the underlying representation learned is a lot better than the underlying MAE representation learned. But if the network is large enough, I guess if you fine-tune everything, you can still get pretty close with MAE. Last one in this category that I want to highlight is the multi-view masked world models. The idea here is to do the same thing, but now with multiple cameras looking at the same scene. Let's imagine cameras looking from different viewpoints. Filling in the blank for other viewpoints requires a pretty deep semantic and geometric understanding of the scene. Philipp will talk more about that one as he's covering a bunch of works that essentially think of this in the context of vision-based robotic control. Let's see, there was a question here up front.
Yes, two slides ago we were looking at the patching for the text. Yes, here.
Mm-hmm.
The patches you also for the text that you mask out. Are you ensuring that do you have to ensure they're the same as the ones from the images? Or
so in this case, these are paired. So it's a paired image and text.
so what the image patches that I do not mask out, do I ensure that my text at least describes that part?
There's no mechanism to ensure that you can fully reconstruct. I guess there's just a hyperparameter, how much you patch out. And so, yeah, pretty high masking ratio allows you to still recover things pretty well. So that's just where the hyperparameter landed. Yes?
Is this random masking in the text? Because that would also determine if you're just masking that's like off and they're not really that informative with things like the red or the answers.
It's random. The masking on the text is random. Yep. Okay. Then let's switch gears to a whole different category. So MAE style works is one thing. Fill in the blank or fill in other channels. It's still I mean, it is one of the most popular approaches today. It's not that old, and it continues to be one of the most popular approaches today. There are other tasks that people came up with. I want to highlight them, even though they're maybe not as popular today. It's interesting to see that they actually gave pretty good results. Relative patch prediction, jigsaw puzzles, rotation, I'll explain them shortly. But maybe the big picture to think about here is that at the time, before MAE, the sense was that reconstructing the image as a way of doing representation learning for vision is not working out. So we need to think of other ways to do representation learning. And these are some of the things people came up with. So context prediction. Here you're supposed to predict the relative position of the second patch with respect to the first. So look at this. On the left, you see a nose and eyes of a cat. On the right, you see what's probably ear of a cat. And probably like the ear that goes in the top right of the image, if the nose and eyes are in the middle, let's say. That's because we understand things about cats, right? If you've never seen a cat or any animals, you would probably not be able to predict that. And so essentially what we're trying to do is force the vision model to understand the visual world in a way that it can reposition things correctly. Part of the beauty here is that all you need is a classifier, right? You just need to classify patches onto, let's say, one of 9 locations. And so as part of the zeitgeist at the time was that it was hard, computationally hard to reconstruct an entire image. Maybe it's just not even necessary. What's a cheaper output I can generate? A classification onto 9-way classification. That's much cheaper. Let me train that and learn in a self-supervised way against that kind of loss. If you look at it, these are not perfectly positioned, right? They're not a perfect, like, equally spaced set of locations. The reason that's the case, and they're also not actually neighboring. And so these things matter. If you make them actually neighboring, you can just look at the texture very locally to see where it matches up, and then that's where they are relative to each other. You don't want that to be the solution. You want a semantic understanding to be the solution to the problem. And same thing, you might say, oh, maybe if you're always in the top right corner, maybe there's some pattern about being top right corner that's not so much semantic about the thing here. And so is there an artifact at the edge of the image or something? So you don't want to necessarily be all the way at the edge, because that might give away where you are in the image. So CNN processes these. That was the state of the art at the time. Outputs, I guess, 8 possible locations because the center is given, and you're supposed to classify the others onto where they might be. We were right. It was the top right of the image. Talk about include a gap, jitter the patch locations, and in fact, the thing on the right is illustrating jitter the colors. So locally, the color pattern might have a certain, due to lighting and so forth, might have a certain pattern to it. You don't want the thing to say, oh, I'm going to pay attention to the detailed color pattern to know that these are actually neighboring right there. You want, again, the confident in this case to understand the semantics of what's in the image. So random perturbations added to make sure the solution is not too easy based on local texture. From there, you could go to solving jigsaw puzzles. You have 9 pieces. Essentially, you can permute these in 9 factorial ways, which is not a tiny number, but it's not a super large number. It's, I don't know, it's maybe roughly like 10,000 outputs or something on your classifier for all the 9 factorial possible configurations. And so that's the output here. And again, make sure they're not actually neighboring and do the right jittering. And so, actually, they're going to 64. Not sure how to get to just 64. You have to look up how that's. Oh no, it's just deciding it's permutation 64. But all possible permutations are allowed. It shows that permutation 64 is the one it decided was the correct output for this one. Then, actually, somebody came out with this thing. All you have to do is predict now the rotation of the image. Image is taken, downloaded. Oh, question.
Maybe after you finish this, but I'm curious how well these techniques transfer to less object-centric data sets. So in a lot of the examples, the object is like very much the clear focus of the image, but in more cluttered images, first, do the representations transfer, and is it possible to learn similarly good representations under like less high quality data?
Yeah, that's a good question. To what extent is the success of NVIDIA's approach is tied to the type of data, which is photography data focused on specific items or subjects, whereas a robot going around the world doesn't have the same kind of visual data coming in? It's a very good question. It's definitely the case that a lot of these things don't generalize that well to data that doesn't follow the photography pattern. Now, that's when they're trained this way and then tested on other data. That doesn't really evaluate the methods. So I don't know if there are such, if somebody would have to collect the data under the other distribution that you have, then rerun the method and see if it still is a good method or not, which I don't know if anybody has really done that. But I do know Alyosha Efros used to have these beautiful slides where he would use this like object-centric data, which are all the data sets essentially, and then use the trained classifier on some random YouTube data, and it would just like be pretty bad at classifying what's in those. So the idea here again is we want to force semantic understanding of what's in the image, but we don't want to label the image. And so if we have it predict which of the 4 possible rotations was applied, it should understand semantically what's in the image, because then it understands the natural way for this, in this case, bird, to be positioned. Now, do you think this is better than a jigsaw puzzle? Do you think it's better than coloring and so forth? It's pretty hard to know. It turns out that this worked the best. Of all these tricks, this is the one that worked the best, which definitely ties into how people take pictures, especially this one. Because, the way you position the camera determines whether this was rotated or not, right? And then they investigated, what if you have more possible rotations? It seems like maybe you could do even better, even a harder classification problem. Turns out that doesn't really help. Maybe like these kind of non-90 degree rotations are just weird and make for a different kind of setting. So you see here, this is on, essentially pre-trained, I think this is probably AlexNet or a similar architecture with this rotation prediction, and then you use the Con4 or Con5 layer to then do linear classification on ImageNet, and you do the best with this rotation network, better than any of the others we've seen here, not better than MAE, which came later, but any of the other tricks that we saw. But at the time, actually, ImageNet using the labels worked even better. This is if you use a different conv layer, so conv1 is the earliest layer. Doesn't do nearly as well, obviously. It does not have as semantic a representation as layers 4 and 5. Then test on Pascal for detection segmentation. Also achieving state-of-the-art here against all of these others that we talked about. Colorization, jigsaw, split brain, colors. All of these are performed by RotationNet, but again, all of these then in turn outperformed by masked autoencoders since then. Also outperformed by SimClear, MoCo, which Philipp will cover later. Okay, let's take our break a bit early today. We'll restart at 25 past the hour, and we'll look at some other pretty interesting self-supervised learning methods.
Okay, so Pieter covered a large variety of methods, but now we'll go into another really popular approach that people have used for self-supervised learning called contrastive learning. So kind of the first success along this line of work was this paper, presented in this paper, Representation Learning with Contrastive Predictive Coding. This was done at DeepMind back in 2018. And the idea that they had here And the kind of setting that they were approaching here is audio, so that's what's being visualized down here. And what we have over here is some context of the audio C and some future chunk of this audio X. And what we've seen before with the reconstruction type objectives is that we might want to try to predict X from C. But in this contrastive type of approach, we don't actually directly predict X. Instead, what we'll do is we'll try to predict some representation of X. And the kind of formulation that they motivate is we want to try to maximize the mutual information between the context C as well as what we're trying to predict in the future. So what that looks like in practice is we can try to effectively look at our context C and then try to match C with this vector Z, our future vector Z, with a bunch of other potential candidates for Z. And you can imagine these future candidates Z are either other audio chunks from various different audio sequences or different audio chunks within the same sequence. And the goal is that we want our context C to be able to match closely with the one that matches in the current sequence. And we would call that a positive example, whereas the ones that come from different sequences or ones that are far away from where we care about, those would be called negative examples. And the way we can compare that is we use some type of distance metric. And the distance metric that they use in this paper is a bilinear dot product, which is essentially just a regular dot product, but we have this additional weight matrix, which gives you a little bit more expressivity. And this loss will be pretty important. This is called, they call this the info NCE, or noise contrastive estimation. And this will come up throughout the rest of this section of the presentation. And so this is what their architecture looks like that they came up with. So they have some audio encoder, G, where they are encoding this audio, and then they have this GRU, which is processing these features to create these context vectors C, and that's essentially aggregating context across this audio. From that context C, they then do predictions across various different time chunks. In this case, they're predicting just 1 step ahead, all the way to 4 steps ahead. And yeah, this is just the info NCE loss that we just talked about. And then you can try to directly maximize this. And then what's in the denominator is they take audio chunks from different audio waveforms that they've sampled in the same mini batch. And so what you're effectively doing in this case is, if you go back to here, you're taking your context C and you're trying to classify it against a bunch of different potential examples. And so it has to learn features that are predictive of future parts of the audio and help it differentiate from other parts of like non-relevant audio. So this is kind of a visualization of what happens after you do this type of pre-training with this info NCE objective. On the left is a visualization of, they take 10 different audio chunks and then they encode it with their encoder G over here, and then they look at the t-SNE visualization. All of the ones of the same color are colored by the this speaker. And so you can see that the model has been able to learn representations that can cluster together different chunks of that waveform from the same speaker effectively. So another aspect of this prediction task is it highly depends on kind of what you choose as how much you're trying to predict ahead. You can imagine if you try to predict way too far ahead in the future, it could be a very difficult task to actually do. And that's what's being represented here. X-axis is the amount of future time steps you're trying to predict into, and the y-axis is the accuracy of how well you're able to predict. So if you're trying to predict immediately after it's much easier to learn because there's very high correlation with the current audio chunk versus the next one, but it's much harder to do it if it's further in the future. This is the kind of speech task that they actually ended up testing on. The left is some phoneme classification, and they also do some speaker classification where you're trying to classify which speaker corresponds to which audio. And you can see that CPC in this phoneme classification does much better than these this MFCC features, is I think some hand design features. It's getting close to supervised, and at least in the speaker classification, it's also getting very close to doing pure supervised learning. Sorry, the way that they learned the classifier for the CPC features is they took the frozen features and they learned a linear classifier on top of those features, whereas the supervised is you train a network end-to-end for the task. And that's a common way, again, just like we were doing in MAE, the linear probing test, where we'll just take the frozen features and then stick a linear head onto it, and then try to learn a classifier from those learned features. So the nice part about CPC is you can actually apply this idea to a whole bunch of different domains. And that was kind of also part of the original motivation for CPC, is they wanted to have a self-supervised method that could learn representations across a bunch of different modalities. And you can imagine that this context to try to predict some future feature task is very general. And this is how they end up formulating it for images. So they take a patch from the image. In this case, they do 50% overlapping, unlike what we saw with MAE. They extract features through it by passing each of these patches through a ResNet. And then they try to predict features that are below that patch in the image. So in this case, this is our context, and we're trying to predict features that are 2, 3, 4 rows below. So visually, that looks something like this. If this is our original image and we patchify it with 50% overlap, we get patches that look like this. And by doing this, we can, at the time, and this was back in 2018. So if you remember when Peter was talking about MAE, we're kind of at 70% over here in terms of 1% ImageNet accuracy. But in terms of back in the day, in 2018, this was state of the art. And they also, test them on, this is looking at top 5% accuracy. Over here, they're looking at some ImageNet features. They pass some images through the network, look at those features, and then compare that to features, or compare that patch across patches of different images, and you can see that it learns these pretty nice correspondences where it's actually learning semantically meaningful patch features and able to do relevant retrieval. They extend this to NLP as well as reinforcement learning. In this case, you can see that this looks very similar to what they were doing in audio, except they so now you can do the same future prediction task as well as have your original reinforcement learning objective. So they essentially add the CPC as an auxiliary loss, able to show improvements. And we'll cover more RL and control-based methods with self-supervised learning in a little bit. So with the original CPC paper, they kind of introduced the idea and showed that it seemed quite promising, as well as the fact that you could use this across a wide variety of domains. Now we'll kind of mainly focus on the image domain because that's where people have been pushing largely with the self-supervised methods as well as these contrastive methods. So CPC v2 is essentially just trying to scale up CPC and get better results. And what we'll see, as we saw with MAE, is that it turns out like a lot of tricks and the right insights can actually go a long way. And it's hard to exactly tell. There's not really much theory motivated behind this beyond just having good engineering. So what they did in CPC v2, it's the same setup as before, except they're using much deeper networks. So before, I believe they were using ResNet 50, and they scaled up to using ResNet 161, so 161 layers deep, extracting out those features. And then again, you have your predictor on top. Your predictor in this case is like a pixel CNN
type architecture. So that way it prevents you from looking in the future, because of course we're trying to predict into the future. So yeah, this is our context C, and then we're trying to predict the features Z of t in the rows below. Again, they're using this bilinear dot product as the distance metric between the feature C and Z with the same info and C loss. For negatives, yeah.
What is W?
W is just an additional learnable parameter. So you could just the regular dot product would just be the Z and C, but you can have this additional learnable parameter to try to learn maybe a more expressive distance metric. Yeah. This is just a thing that you can like add or remove, and they find that it helps at least with their downstream results. Importantly here, they have, when they take their negatives or the things that they're trying to classify against, they have patches across other images as negatives, but they also have patches within the same image as negatives, just not at the rows that they're predicting. So I think specifically for this, they just tried to predict only 2 rows ahead, and everything else is considered a negative. So you can imagine that makes the task actually a little bit more difficult, because now you have to know exactly what would be like 2 rows below the current patch. And again, that's like a common theme that we'll see, that if you have to make the task just hard enough, that the model has to learn like really good representations, but you can't make it too hard where it's literally impossible to learn, and you also can't make it too easy where the task is too trivial. So there's like always a balance here with how these tasks, these pre-training self-supervised tasks are defined. So some additional tricks that they do, they train for much longer. In this case, they're training for 500 epochs, which at the time took about a week. And you can imagine, yeah, compared to some of your homeworks, is way longer. They're doing a lot of different augmentations to their images. So they're doing like spatial and color augmentations. And again, this number of negatives is very important. So these are the different downstream tasks that they test. So they do this pre-training that we just described. They do this linear classification on ImageNet. You can also investigate efficient classification, where you don't provide all the labels. You provide maybe 1% or a smaller amount of percentage of the full labels to your tuning task. You can also try this on transfer learning tasks, where these models are pre-trained on ImageNet, but maybe we want to test it on like Pascal VOC, which is like a bird classification data set. So here are the results on ImageNet, linear classifier score, and we see that we've gotten huge improvements from what we saw before. So CPCV1 was sitting around 48%, but with CPCV2, we've gone all the way up to 61%. Of course, you know, the model sizes are much bigger, so it's a little hard to directly compare. If we look at a similar model size, we see that brings us back down to 63.8. But still much better than what we were seeing with CPCV1. So here are essentially all of the model improvements that let them go up from CPCV1 all the way to CPCV2. I won't go into the details of those, but yeah, you can look if you're interested. So what this plot is showing is it's showing the red curve over here, which is just ResNet trained on pixels from scratch, versus this blue where you first pre-train ImageNet, and then you fine-tune on a certain percentage of the labels. So in this case, we only have 1% of the labels. This is fully supervised. This is first unsupervised pre-training, followed by supervised fine-tuning with 1% of the data, all the way up to 100%. And kind of what this motivates is that it's always advantageous to do some sort of unsupervised pre-training on your data set. Even at 100%, we still see a small amount of gain by having the unsupervised pre-training step. And at very small percentage of labels, you can see that's very, very helpful. And so this suggests that with unsupervised pre-training, we might need a lot fewer labels and can be much more data efficient. And kind of that's definitely what we're seeing the trend nowadays is with massive internet data, we can get a bunch of unsupervised data, and that's really helping for these downstream tasks that we care about. Cool. So that's CPC. And next we'll investigate instance discrimination. So what we were looking at before is we were trying to contrast part of an image with another part of that same image. But what we'll now do instead is we'll try to look at an image. In this case, this is the dog, and we'll try to compare that against other instances of the same dog versus completely other different images. So here's a dog, we've made a grayscale, and here's the same dog, we've kind of flipped it and then zoomed in. And we want those to have similar representations, whereas we want this dog to have a very different representation than this cat. And these methods will be MoCo and SimClear. So the first one is MoCo, Momentum Contrast for Unsupervised Visual Representation Learning. Again, this one is from Kai-Ming. This was done in 2019. So Kai-Ming was working on this unsupervised pre-training back then, and at the time he was working on this contrastive type objective. The work that Peter presented earlier, MAE, was done in 2021, a few years later. And so Kai-Ming would first spend some time in this contrastive type objective, and then later would work on the reconstruction objective, which we saw had a lot of success as well. The idea with MoCo is, again, we have our image X, and we're going to pass it through an encoder to get some query. And we want to compare that against augmented versions of itself as well as random other instances. The issue here, however, is if we want to have a bunch of things to compare to, that means we need a huge batch size. And at the time, we didn't have the types of scalable computing infrastructure that we did today. And so it often means that if you want to do this type of contrasting, because we're contrasting now with full images and no longer patches, which can get you a lot more samples to contrast against, you were getting like really small samples. And so that made this type of like contrastive idea not really work. And so the insight here instead is we can take a history of a bunch of keys and then cache them in a queue, and then contrast against this queue of samples. And there's a couple of tricks that are necessary to get this to actually work as well. And so part of that is now we actually need to have this add momentum to this encoder. So we can't take our query queue, pass it through the encoder, take an augmentation and pass it through the same encoder. We actually have to pass it through this polyact average version of the encoder. So this is looking at MoCo in a little bit more detail. So we take our observation, our image O, and we apply two different augmentations to it. For example, like we saw, we can turn it to grayscale, or we can flip it and zoom in. We take our feature extractor F, and then that gets our query Q. And then the way we get our key is we pass it through this polyact average version of our encoder, which is essentially just an exponential moving average of the weights of the encoder. And then we apply the normal info NCE loss. And again, we are actually keeping a queue of all these keys. So once we extract out this key, we keep a long buffer of these keys. And we use that in our negative examples. So yeah, I think the best way to understand this is probably just look at the code, which is actually quite simple. So we can quickly walk through that right now. But essentially, we have our image X. We pass it through a random augmentation, and we get these two different augmentations. And we pass it through our network here. We have FQ, which is the key network, and then the query network K here. So that gives us our two examples. We then just do a matrix multiply to get the dot product. And then that gives us our logits. And then we try to do the info NCE, which is effectively just cross entropy. We're trying to label that this image should match this augmented version of the same image and not match all the other images. And then the negative examples we just take from our queue, which is of this size. Yeah, we just take the cross entropy loss. And then you can see over here, here's where we deal with our queue. We then enqueue the new keys that we got from this current batch. And then we dequeue if necessary. So like once we filled up our buffer, we want to remove out the old examples. Yeah.
So is the design of this largely dependent on how well you choose your augmentation?
Mm-hmm.
So that's basically the crux of like your tuning, is really figuring out what is the best augmentation here, so it's not too easy to learn, but also not too hard to learn.
Yeah, that's correct. So I think one thing with this type of contrastive objective is you want your feature representation to be agnostic to, like the representation you're trying to learn should be agnostic to something, and in this case it's like these augmentations. And so the way you choose these augmentations matters a lot. And it also matters especially a lot for your downstream task. And I think that is one thing about self-supervised learning that people don't talk enough about, is that oftentimes I feel like it will heavily depend on what you care about in your downstream task. A lot of time we just treat it as, oh, you can do some type of generic pre-training and that'll magically improve on your downstream task. But it should be that your pre-text task has some type of overlap in terms of what you actually care about for your downstream task to actually get it to work well. And in this case, for these classification types tasks, where we care about these more object-centric type features, it turns out that these type of very basic image-based augmentations seem to work out pretty well.
So just out of curiosity, like when you looked at the mask autoencoder stuff earlier in the lecture, those are like very aggressive, right, in terms of the masking.
Mm-hmm.
How aggressive are they with the augmentation, right? Like, you know, typical ones are like color jitter, rotation, random cropping, all of that. How aggressively do they augment, or not very aggressively here?
They do pretty aggressive augmentations, I would say. I mean, yeah, so usually we'll see that people will try a whole bunch of different types of augmentations, but then generally they do very heavy cropping, or at least one part of the image will be very heavily cropped, as well as, yeah, this type of color jittering, rotation, flipping. Yeah.
Thank you.
Mm-hmm. Yeah, I will talk about that right now. So we can maybe view potentially different ways that we could take this approach. So you just asked the question, why do we need momentum? Well, maybe we don't need momentum. So one potential approach that we could take is we have our single image, we get our key and our query, pass it through the same encoder, and then we can just do our info NCE loss here, our contrastive loss, and then backprop through both. The issue that they had at the time is it's really hard to fit a big batch size just due to compute limitations. And so the way that you want this to work well with this contrastive loss is you want to have a large batch size so you have enough negatives to compare against in order to learn semantically meaningful features. Because, for example, let's say if we go to limit, you only have one in your batch, the task is trivial because you can always classify against yourself. And so you really need a really large batch size for this to perform well. So given that we want to maybe have some type of trick to keep a larger batch size, maybe it makes sense to have this memory bank. And that's what we could potentially do over here. The issue with having a memory bank like this as your target is you might result in some type of like collapse where you have your encoder over here, but then these things are always fixed. So what they do with the momentum encoder is you're trying to take your image X, you pass it through this momentum encoder, which is a very slowly it's a slowly moving average of your encoder weight. So you can kind of treat this as a more stationary distribution. And so you're giving it something a little bit more static that the encoder has to match against. And so that helps stabilize training and prevent collapse issues. And so that was kind of like the motivation for why they came up with this memory bank plus the necessity to have the momentum encoder. And we'll see that this is a common theme with a lot of these types of methods, is that because we're kind of trying to predict in some latent space, there's all these potential issues of collapse. And having a more slowly moving target can help stabilize things. So This is this is the accuracy on ImageNet that we're showing over here. This is, and they compare against the different approaches. So end-to-end is what we just went over here. This is A. And you can see that they're only able to scale up to a batch size of 1024 before, like, compute-wise, at the time, they weren't able to scale further beyond that. If you just use the memory bank, you can see that the performance is actually a bit lower down here. And if you use MoCo, which was the very one on the right, you can see that it actually just matches the performance of the end-to-end approach, but it allows you to much easily scale to huge batch sizes. They were able to scale up to 65,000. And yeah, able to scale up and get top ImageNet accuracy at the time of their release. So next we'll talk about SimClear, which is very similar to what we just covered with a small change. So we just talked about MoCo, where they have this momentum on part of their network. So SimClear gets rid of that, but they make an additional change. And what they do is they add this additional G network, which predicts the feature Z that we're trying to contrast against from our representation. So whereas in MoCo, we directly used the feature that we contrasted against as our representation, here they're learning an additional network to map that. So with this trick, it turns out that you don't actually need the momentum encoder. Process-wise, it looks very similar. It's hard for me to show, I think, without... but yeah, effectively, the process looks the exact same, except now... the process looks the exact same. Except now, because we have removed this asymmetry with the momentum, you can actually just do things both ways. You can take x1 or xi and xj and actually flip it as well. And so that's what we see over here. They do one augmentation on the image, process it through the network, take the second augmentation, process it through the network, and then take the loss, where they take the loss both ways. So SimClear was very effective and able to outperform MoCo, and kind of removes this additional complexity of the momentum. I'll skip ahead here. So yeah, this is kind of like a more direct comparison of the SimClear approach versus the MoCo approach. On the SimClear, this more complete end-to-end approach, where we process these frames and are able to do contrastive on everything in the current batch. Whereas the momentum contrast lets us pass less examples into the encoder because we can keep a huge queue of negative examples. And the trade-off, I guess, you can think about as more of just like a compute trade-off in terms of what you're really able to have. And we'll see that MoCo later on actually gets rid of their own negative queue and does something more similar to SimClear with better compute, because now we can just do everything with the current batch. I'll skip some of this because of time. So with MoCo v3, they state themselves that there's nothing extremely novel in what they're proposing here. They just give some engineering tricks and scale up to using vision transformers, which were working very well at the time. Yeah, I'll spare the details of the code, but effectively the main changes that they make is they remove the momentum, they remove the negative buffer and momentum is still kept, and they replace the network with a VIT. So they noticed that when scaling to a VIT, you actually result in a lot of instability, and that's seen over here, where when we increase the batch size, you see all these blips in training. This also happened regardless of the learning rate. And they kind of proposed, when they were monitoring these training curves, they noticed that these gradient spikes would first happen in the first layer of the network, and then a few training iterations down the line, it would happen in the later layers, or the last layer of the network. And they hypothesized that this instability could be just due to too much changes happening up earlier in the network, and then that later propagating down the line. And if you have these gradient spikes, you're effectively like unlearning some of the features. And so their goal was to try to avoid that, and the way that they did that is instead of having a learned patch projection, where when you take your image patches in the VIT, you learn it with like a linear layer, they just use a random layer and they freeze that. So you can't learn that projection anymore, and so your representations into the VIT are fixed. And they find that just fixes the issue. And now you no longer have these training blips. That's the green curve showed here, whereas the blue curve over here has these training blips. And you can see that for these larger learning rates, we're able to get pretty much higher performance, like 2 percentage points on ImageNet is pretty big for just this simple change. And this is a trick that down the line other models will also use, and they find it helpful. Cool. So the next model in this line of work that we'll cover is BYOL, or Bootstrap Your Own Latent. The approach here looks very similar to what we've been seeing, where you're taking two views of your same image and then passing it to get a representation, and then we project it to a new feature space. What they're doing in addition here is they're adding an additional, what they call a prediction network. And then instead of doing a contrastive loss, they're actually simplified it to using an L2 loss. So now, after we pass our first augmentation through the image, we normalize it, we get our normalized Z, and we get our normalized Q from the target network. And then we can use an L2 loss over here. Effectively, this is just a cosine distance loss now that we've normalized things. And again, this target network is an exponential moving average version of our original weights up here. So this seems nice because we're able to remove the contrastive component. Now we can just simply do this feature prediction with an L2 loss. And that seems much easier than having to go through all the complexity of having like the info NCE loss. And it turns out that it also seems to perform much better as well. So here's comparison of using a ResNet 50 encoder. Top one ImageNet accuracy is now at 74%. And if you scale that up to ResNet 200, we're able to get 79. One other nice component of BYOL is that it seems to work well even with smaller batch sizes. So with SimClear, one thing that was the end-to-end approach that we were talking about earlier. With SimClear, it seems that when you reduce the batch size too low, you get a massive drop in performance. That's what we kind of show here. If we go to too small batch size, we get a decrease of up to 4% accuracy. Whereas the decrease for BYOL, it seems a bit more robust to that. And we see that BYOL also seems more robust to the amount of augmentations that we're applying to our images. So here's another perspective on what BYOL is doing. So it seems weird that we were able to magically get rid of the contrastive loss, yet the model was still able to learn features that could be predictive without being trivial. Like one potential issue of removing the contrastive loss is if you're not trying to push away examples in your negatives, then you can just map everything to the same point in your feature space. For example, if you map everything into 0, then you can get perfect L2 loss. But then you haven't really learned any useful feature. So, So it's kind of weird that BYOL actually is able to do well. And the authors don't mention this or study this exactly why in their work, but I think this is a pretty interesting intuition, which is what actually is being used is in their MLP projection networks, they have this batch norm. And what happens is you actually remove this batch norm from the BYOL prediction network. Performance basically just drops to as if you were using some completely random feature. And if you actually investigate the learned feature Z, it turns out that it does collapse and it's just being mapped to the same point in the feature space. And so what's actually happening when you're using this batch norm, it turns out, is it's probably doing some type of like implicit contrastive learning. And that batch norm is what's needed to prevent this mode collapse, because now when your features get mapped through the batch norm, you're subtracting the mean and then dividing by the standard deviation, and so everything gets kind of renormalized back out. And so you're comparing essentially to the mean of everything in your mini batch due to the batch normalization in the network itself. So yeah, here's just like a quick summary of the different methods we've covered so far. SimClear does everything end to end. There's no need for any momentum, but generally you'll need a pretty big batch size. In their MLP network, they actually use batch norm within the layer as well as at the output. Moco looks very similar, a couple of differences being the momentum that they use for their target network, as well as the memory bank. The memory bank is gotten rid of in Moco v3, and they just use everything in the same batch like SimClear, but they still maintain the momentum. But with the momentum, you can see that you can get away with not having any batch norm in the MLP. Or sorry, I mean, we need the contrastive loss for that. Batch norm is different. Batch norm, yeah, but they don't use batch norm here. With BYOL, we see that they don't use the contrastive loss, but they still have this batch norm here, as well as the addition of this additional prediction network. So next, we'll talk about some distillation methods, which will look very similar to what we've seen, except they will kind of try to get rid of the contrastive loss. And we can kind of see BYOL is already in that direction. They don't use a contrastive loss, so maybe it would be better to put BYOL in this section technically. But these type of approaches will aim towards moving the contrastive loss. So Dino is one of the works in this line that produced very good results. So first, let's consider knowledge distillation. You can consider knowledge distillation as having some teacher network, and then let's say you pre-trained something on ImageNet and you want to distill that into a student network. Maybe you're trying to have a smaller network that can still get the same performance as the teacher network. So the way you can do that is pretty simple. You just go through all the examples in your data set and you try to have the student match the output distribution of your teacher. So yeah, we just try to minimize the cross entropy between these two distributions, which just looks like how you would normally do. But instead of having like 0, 1 labels, you would have the labels from the teacher. Yeah.
I don't understand this teacher-student thing. So like in your other examples, right, like we would run the random augmentations on two things and then try to match them later. Here, if you're giving them the same input, right, you're giving them both X, then I don't understand what's happening.
Yeah, sorry. We haven't got to the self-supervised part. I was just trying to introduce this idea of knowledge distillation. So like a more typical example would be you have a frozen teacher. Let's say you pre-trained it on ImageNet and you get really good results. But let's say it's a ResNet 2000 or 200 and you want to have a ResNet 50 that can get the same performance. You can try to distill your smaller network to achieve the same performance as your larger network. And so in this case, your teacher would be frozen. You just pass in images X into your teacher and you have your student try to match that distribution. So this is like a more typical case of where you have like a knowledge distillation. Or for example, let's say you have a language model. You want your Llama 7B to get the performance of the 70B model. You could just take a bunch of examples, freeze the 70B, and then try to have the 7B model match the same distribution as the 70B model.
So basically the teacher is a pre-trained large model and the student is just trying to match it?
Yeah, in this supervised setting. Yeah.
Is this a typo, or is there a reason why GTheta to use the student and GTheta S is the teacher?
That's a typo. Thanks, I will correct that. Or let's just correct that now. Okay. So Dino tries to take this approach, but then apply it to a self-supervised setting. The issue now comes as we don't actually have a teacher network, so we don't have anything to map to. We only have the network we're trying to learn. And yeah, so they try to do some tricks to get that to work. But as you can see, kind of now we're back into this very similar setting that we saw before, where we have our image X, and we now are applying two different augmentations to it. So the path for the student side happens in the same manner. We pass our image through the student G, and then we get some distribution over features instead of just a feature itself now. Now we're treating these as distributions. The trick for how we get our teacher is we're, again, going to use an exponential moving average of our student network. And the intuition there is we want to try to stabilize what the teacher network is. We don't want the teacher distribution to be moving too much. We want to have that relatively be stationary. Of course, it's being updated as the student learns more, but it's going to be more stationary compared to the student. And yeah, we're going to apply this. We'll ignore the centering part for now, but then we'll produce some distribution. And then we want to try to match those distributions as with the knowledge distillation. So here again, just like with BYOL, we have nothing really to prevent collapse. And that's, yeah, and that's where the centering parts come in. And so what's happening in this centering is you subtract out the mean to kind of recenter your distribution. And you can see in the pseudocode, we have our augmentation, our two augmentations of our image X. We pass them through the student and teacher, and then we apply the cross entropy loss over here, our knowledge distillation loss, and then update. But then we have, oh yeah, so we also do the polyact averaging for our teacher parameters. And then we have this additional C, which is the way that we center the distribution. And the way that we center the distribution is we look at a history of the features from the teacher, and we create an exponential moving average of those features. So that written out kind of looks something like this. We have our image and we apply these two augmentations to it. We get these distributions from both sides of the network, and then we try to minimize this cross entropy. And this centering step is important to prevent mode collapse. And after this training procedure, they apply to a wide variety of different tasks. We'll just look at a few. So for example, you can get these nice segmentations completely unsupervised. The way that they do this is they just look at the attention mask and they threshold it on the CLS token. And then they compare some similarity to a ground truth mask. And you can see that Dino is able to actually pay a lot more attention to objects within the scene compared to a supervised VIT network. With linear and K nearest neighbors classification on ImageNet, you can also see that Dino is performing quite well with 75% linear probe accuracy. With ResNet 50, if you're using a VIT version, it's able to get even a little bit higher with 77%. They also looked at these saliency maps, looking at the self-attention for a variety of reference points. And you can see that it's paying attention to semantically similar parts in the scene. And able to pay good attention to like objectness and kind of ignore background. Yeah, maybe it's helpful to look at some differences of Dino compared to these prior methods that we've looked at. So cross entropy is the loss that we saw that we were using earlier in order to do the matching, but you can imagine that you could potentially also use MSE loss. Turns out if you use MSE loss, you actually get a reasonable drop in performance. And so having this distillation loss is pretty important. If you remove momentum, you can see that that instantly results in collapse. And so having a more stable teacher is very important. So with iBot, they took this idea that people were using in Dino, and they thought if we're trying to find the distribution of just the features of the image, can we also do it at like a more granular level? Can we do it at a patch level? And that's exactly what they do. So for each augmentation of the image, you have your online tokenizer or your online network take in all the features. And then you have your student network take a patchified version of the images. And when you pass it through the network, you, just like before, try to do the distillation at the image level by applying the feature on the CLS token of the VIT. But then you can also apply the same loss, but on the patches the patches that you passed into the student. So the student will have a certain amount of patches that were placed here. There's some that have been masked out, but you can try to match it with the full version that the teacher has seen. And the teacher got to see all of the patches. So now you're trying to effectively learn a feature that can be predictive of something that has seen, of features that have seen the entire image. And this trick enables you to outperform Dino and scale well, getting up to 81% ImageNet linear probe accuracy. We'll just quickly glean over Dino v2, but effectively they take the idea of iBot and add a bunch of other tricks and able to further push performance. And you're able to get even better these type visualizations. And this is a visualization of the first principle components of the output features. And you're able to do these very nice self-supervised tasks, as well as use it as pre-training for further downstream tasks like segmentation and depth prediction. So in the next line of work that we'll talk about is JEPA. So in JEPA is this approach that Jan LeCun proposed in his paper in 2020 or 2022. This paper is really big, and it proposes kind of Jan LeCun's thoughts on the path, like a huge proposal on various different types of machine learning and how to build one really big cohesive system. So JEPA is only a very small part of it. It's not the entire part. But effectively what he's saying here is that he believes that the way that we should be doing unsupervised feature prediction is by so there's different ways that we've seen us to do the self-supervised learning so far. And the way that Jan LeCun thinks that is most promising is we take our image X, pass it through our encoder, and instead of directly predicting Y, we want to predict in this latent feature space. So we passed both our X and our Y into some latent space, and then we try to predict Y in this latent space. We try to predict the latent space version of Y from the latent space version of X. So one motivating example is, for example, let's say X is a video clip of a car. These latent space representations might be like semantics of the car position and the car velocity. And then maybe the prediction is, and we want to predict the future latent space. But we don't really, if we were trying to do it in raw pixel space, we might have to worry about semantic or low-level details. And kind of, maybe that might lose out on some of the semantics. But ideally, our encoder is only paying attention to the semantically relevant information. And so that means we would hopefully only need to pay attention to like the car position and car velocity, rather than focus on smaller level details like how the leaves in the background are moving. Yeah.
I'm very confused about this. So you encode the input data and the corresponding label, and then you take that to a latent space? Wait, so you encode the input data, take that to a latent space, and then you predict its label within the latent space, and then you take the true label and encode that into a latent space and see if it matches your latent predicted label.
Yes. Let me move ahead to here. Maybe this will make more sense.
Okay.
So what we've seen with the contrastive learning so far is it looks something like this joint embedding prediction. Let's say MoCo or SimClear, we have our image X, we pass it through some encoder and we get some feature. And then we try to do like cross entropy, for example, or contrastive learning, for example. In these generative architectures, for example, let's say VAE that we've seen, we first have, or MAE, we first take our image X, we encode it, then we pass it through a decoder to try to recover the original image X. Or, yeah, the original image, or the original something. And for example, this could also be like a class. I mean, he tried to formulate this in a general example, but in the case that we're looking at, just say that these are both instances of the same image or augmentations of the same image. And what this joint embedding prediction architecture is saying is we pass it, everything is being passed into this latent space, like in A, but we have this like additional predictor network that is trying to predict on top of our X. So we try to do some additional prediction on top of what was given, but we can potentially condition on additional latent variables to try to model uncertainty. Z is like a random variable, yeah. Does that make sense, or kind of? So maybe one other way to see this is if we looked way back to the comparison between like MoCo or SimClear versus BYOL, BYOL had an additional prediction head on top of the feature space, and you can see that as effectively what Jan LeCun would call like the predictor over here. So you just have like an additional head that you're predicting off of in the simplest case. Sorry? Z in here is just a random variable that you can potentially condition on. They don't actually use it here, but you can just treat it as additional noise to model like a distribution if there's uncertainty. So yeah, in this paper, IJEPA, they try to take this type of approach and then apply it to learning self-supervised features from images. Specifically, what they're doing is so now again, remember, we're in this situation where we have some X and some Y. In this case, X is what is called context and Y is called this target. And what we want to do is we want to try to predict the embedded features of we want to try to predict the embedded features of our target from embedded features of our context plus some predictor network. So we have a common context encoder, which in this case is a VIT network, which takes patches of the image. And we produce those feature representations. And then now we want to try to predict at these, so this is this gray box over here. We pass through our encoder, we get our gray features for that part of the image. And now we want to try to predict these parts in the target. And the way that they represent this is that they represent these as mass tokens. So they pass this context as well as their mass tokens to get predicted features from the target encoder, and then they apply an L2 loss across these different features. So this should look similar to BYOL, but then they've kind of structured the task a little bit differently, as well as like the architectures and stuff that they're using. So here are examples of how they construct their context and their targets. So they first construct their targets by taking the original image and they sample these random blocks in the image. Then they essentially sample random blocks for the context and then subtract out the ones so there's no overlapping blocks, and you effectively get that as your context that they use. And that's how they construct these training pairs. So if you train your model with this procedure on a large data set, you're able to get very computationally efficient results. And so what they're showing here is the number of GPU pre-training hours versus top 1% ImageNet evaluation. And one advantage of a type of approach like this compared to something like MAE is you don't actually need to do reconstruction, which means that everything is operating in a latent space, which means that it could potentially be a lot more computationally efficient as well. So yeah, we see good performance over here, despite being only trained for 300 epochs compared to MAE, which is, let's say, being trained for 1,600. Another thing that they can do here is they can try to, even though we did the pre-training in latent space, we can try to learn a model that does reconstruction given the encoded latent. So this is done after the pre-training step, and effectively they learn a conditional diffusion model, which tries to learn how to do diffusion based on these learned representations. And these are the representations that you see over here. You can see that it's able to effectively capture that there's a bird here, kind of its location, how it should be posed, but it kind of doesn't pay attention to things like background detail, what color the background should be. Same thing with the dog over here. You can see that the pose and everything of the dog is very correct, even if maybe some of the smaller details and stuff are missing. And so that information is at least present in the representation. So VJEPA is a follow-up, which was just released 2-ish weeks ago, I think. And they apply the exact same idea, but in the video space. I think due to time, I'll just skip over it, but if you all are interested, the details are there. So next we'll talk about CLIP. So CLIP kind of opened us up to this age of self-supervised learning using text-to-image pairs. And I'm sure you all know of CLIP, but this is how they actually did it. So just like before, we want to take we have some X and some Y, but instead of being an augmentation of the same image, they're actually different modalities of a pair. So we have image and its corresponding text pair, and then we're going to apply our contrastive objective where we try to classify the correct text with the correct image, and vice versa. And all the other examples in the batch are treated as negative examples. We want to have that feature try to be different. And once you have this pre-training objective, hopefully your feature is your image features and your text features are very good at are very aligned, which lets you hopefully do something like downstream classification very easily in a zero-shot manner. And how you would do that is, let's say we're trying to do ImageNet classification. We can take all of our ImageNet classes and then create a text label for it. For example, we have like playing car dog here, and then we can make a caption, a photo of a dog, and then try to contrast these text labels against the feature from our image encoder. So at the time of CLIP, there weren't that many really good open text image data sets. In their paper, they mentioned that there was this one, YFCC 100 million, but they mentioned that there's a lot of pretty low quality captions from the metadata in that data set. Like this is one of the captions for the data set, which obviously doesn't contain any semantically meaningful information. So they ended up constructing their own data set of 400 million image text pairs, which is proprietary. And they did this with some like automated searches with some generated queries. The code and implementation for CLIP is very simple. You just have some image encoder, some VIT, and some text encoder. And you pass that through for all your images and your text. And then you get these corresponding features, normalize them, and then you get dot product. You apply dot product to get your logits, and then you just apply cross entropy, and you apply it both ways. So yeah, then this lets you have really impressive at the time zero-shot capabilities for classification. So they tested it on a whole wide variety range of different classification tasks. On the right here is showing zero-shot CLIP compared to a fully supervised linear baseline. And you can see that their zero-shot baseline is able to do better than if you do like a fully supervised version. Of course, it's not exactly comparable. This is only a fully supervised version of a linear classifier fitted on the raw data, but still it shows that this pre-training is very effective. Cool. So in addition, beyond just its usefulness in zero-shot classification, it can actually be a very useful feature for downstream models. So we saw earlier in unclip, that you can use the pre-trained text encoder to get those text features that we can then use to condition on for image generation. And we see a lot of VLM models today, vision language models, will actually use a pre-trained clip model to encode the image into some amount of tokens, and then that's passed into the language model. So yeah, these features are useful in other settings as well. Okay, I will skip over lit and clip. And since then, there's been lots of different extensions of clip just because of how useful the model is. So one that I think is quite interesting is this one called Flip. Again, from Kai Ming at FAIR. He's the last author on this one. So this was done after MAE, and his observation there was with MAE, like this masking is a very effective strategy in terms of speeding up computation. You only need to do computation on your unmasked patches. And so the thought was if you can apply this type of strategy to clip training in some sense and see if that improves things. And you can see the benefit over here. So over here in gray is if you just apply the normal clip or their clip reproduction. Then if you apply 15% masking strategy on the image, you get this learning curve. The y-axis is ImageNet 1% linear probe accuracy. And if you apply 70% masking, you get this learning curve over here. And so you can see that you're able to get, you're able to train much more efficiently. If you're looking at this same final performance, you're able to get like a 3.7x speed up time. And for the same amount of training hours, you're able to get a much higher performance. So one thing that you do have to be careful of if you do this is that there is some train and test time mismatch, because in train time, we're masking parts of the image, but at test time, we want to see the full image. And so what they do mention is you have to do this unmasked fine tuning, where after you do your pre-training for, I believe it's like 0.3 epochs, you do a full end-to-end fine tuning with seeing the full image. It matters most for if you're doing a very high masking ratio for 75%. For example, you see this huge gap here. It matters less if you're using a smaller mask ratio like 50. So we've covered a large variety of different methods, so you might ask if there's any ways we can combine these methods. SLIP is one approach that does this, done by Norman here also at Berkeley. And yeah, the idea is quite simple. Let's try to add on some self-supervised learning on top of CLIP to see if the self-supervised learning objectives are able to help. So SLIP is their method shown over here, and you're able to get a 5% boost in terms of the zero-shot performance if you apply some self-supervised learning losses. With pure self-supervision, there is no zero-shot capability, so it's not shown here. And with linear classification, you see that there's a benefit as well on top of CLIP or just using pure self-supervised learning. The algorithm is pretty straightforward. They're using SimClear as their self-supervised learning approach here. So again, we have our two augmentations because we need that for our self-supervised learning approach. We embed these features to get our predicted values or our latent value Z. And then we can apply just the normal SimClear loss and the normal CLIP loss and add them up together. And that's shown over here on the right. And we can see that that helps across a wide range of different architectures as well, and scales correspondingly across VIT small, base, and large size models. The next one I'll quickly cover is Cacao. Contrastive captioners are also image text foundation models. What they do here is they apply this captioning task to try to learn an image encoder and a text encoder. And they're actually able to achieve the top 1% accuracy, state-of-the-art 91%. This was state-of-the-art for quite a bit of time. I think it's been taken over now. But yeah, this is very good. Okay, I'll skip over the, yeah, so essentially the idea is very simple. First, we're going to do the contrastive loss like we did with clip. So that's what's shown here. We pass the image, we get some CLS token feature. Same thing with the text, and we do contrastive loss. In addition, we're going to have this multimodal decoder head, which is going to try to recaption the image. So with clip, we just had this caption, but now we can apply a shifted version and do next token prediction to also try to predict the caption given just the image. And they find that, yeah, this is able to get really good results on a huge a variety of different benchmarks. Let's see, how much time do we have? Okay, I will skip over these, but there are some other interesting approaches that people took, if you all are interested to take a look later. So next, I'm going to briefly cover different ways that we can use self-supervised learning in reinforcement learning and control. So the first one, this was done by Arvind, who is one of the original instructors of this course. Curl, contrastive unsupervised representation for reinforcement learning. So architecturally, we'll see something very similar that we've seen before with the contrastive methods, where we have our observation and we have our two separate feature encoders that we are applying our contrastive loss to. But again, remember, now we're trying to do some downstream reinforcement learning. And we take the features Q from our encoder and we do normal reinforcement learning on those features. So for example, if we cross out this reinforcement learning pipeline, it would just be normal contrastive learning. And if we can cross out this contrastive learning part, it would just be normal reinforcement learning. The motivation here being that potentially this unsupervised objective can help us get more bits and more information learning-wise for our downstream RL. So yeah, the approach is very similar. I'm not going to cover the RL because that's out of scope for this course, but we can talk about how the unsupervised learning helps the downstream RL process. So here, the augmentation that they find most helpful is crop. They tried a bunch of different other augmentations. And as we were talking about before, the downstream task actually matters. And so a lot of these more color-based stuff, at least for this type of task in these simulated Majoko environments, doesn't really matter. But maybe caring about more spatial relationships actually matters. So crop is the one that they were using. They were using, again, cross-entropy loss. And then they tested a couple of different settings. So one is to use the exponential moving average or without. Again, we need that exponential moving average to get good performance. And then there's using of what type of loss to use in the distance metric. So there's the bilinear versus direct, or using direct cosine distance, and bilinear is also quite helpful here. So on the left over here is running curl versus SAC. SAC is the base algorithm that they base on, and curl is adding the representation learning on top. So state SAC is just using the raw underlying state of the environment, whereas curl in red is training from raw pixels. And what you see over here is that the one with curl is able to match the gray curve almost for all of the environments. And that's pretty impressive because curl actually doesn't have the access to underlying state. And so you're able to essentially match the ground truth state information performance by just looking at the pixels. And here's corresponding performance on comparing to a couple of other different algorithms. And you can see that curl is able to perform competitively in this setting as well. So next we'll look at R3M. So the motivation of R3M is we want to look for robotic manipulation. We want to have some type of pre-trained visual representation. A common strategy in robotics is to take a pre-trained ResNet on ImageNet and then use those features. But of course, those ResNet features are trained on like trying to do random classification, and so might not pay attention to the certain features that we care about for robotics. And so maybe if we think about the data and the pre-training, we can get a better representation for the types of robotics tasks we care about. So what are the types of things that we might care about? One is temporal dynamics of the scene. So hopefully our representation should be somehow knowledgeable about how states transition to other states. Another important feature might be how relevant or pay attention to things that are semantically relevant to various tasks that we might care about, such as objects and their relationships to each other. And another one is just to be compact. So the data and the process that they use here is that they're going to use Ego4D as their pre-training data. And an advantage of this is it has a lot of in-the-wild data that's egocentric viewed, and it has language annotations as well. It has a variety of different, lots of video data from very diverse locations. So again, we're going to apply this idea of contrastive learning, but in a slightly different way. So what they're doing over here is they're doing time contrastive learning, and they're encoding temporal dynamics into the representation. You don't have to look into the loss too closely, I'll just explain the intuition, but effectively what we want is we want frames that are closer together to have a representation that is close to each other. So we want this to be a positive pair, and we want some frame that's very far away from our anchor to be a negative pair. And that's effectively how they decide to choose what's a positive and what's a negative pair. The other one is to have video language alignment. So these videos are annotated with the language of what a language action of what is happening in that video segment. And again, this alignment should, and the intuition here is we want the alignment to increase over the course of the video. If we're doing some action, hopefully that language annotation should be more accurate the further we get into the video. As well as the language should match with the current video, but should be far away from other different videos. And again, we can apply a contrastive like objective to achieve that. Then we just throw all those terms together in our loss, and then we apply some regularization as well. So there's an L1 and L2 regularization to encourage some types of sparsity. These downstream tasks that they test on is just imitation learning. Imitation learning, you can just think of, you have the ground truth state as well as the action, and they test across these wide variety of different environments. And these are their baselines. So MoCo, which we saw earlier, MoCo, and we have clip representations, we have ImageNet supervised representations, we have representations trained from scratch. And you can see that they're able to, that these R3M representations are able to do much better on these robotics tasks. MoCo 3, 4, 5 just means that they're taking the intermediary features at those parts, those, I think like the third to last, fourth to last, and fifth to last layers. So we saw these types of contrastive type objectives being used. Can we use one of these reconstruction type objectives that Peter was talking about earlier? So that's what was done in this masked visual pre-training for motor control paper done by Tete and Ilya at Berkeley. The idea is to try to apply MAE to learn features for robotic control. And they have a procedure that's very similar to MAE, where they're taking a large video data set of egocentric hand-focused type data that has a lot of object interaction that might be more relevant to robotics, and pre-training and MAE on that. Then downstream, they're taking those representations from their encoder, this frozen encoder, and then trying to learn a policy on top of that. The specifics, we don't have to get into detail. This is the data set combination they did. They did Epic Kitchens, YouTube, 10 Days of Hands, something something to something. And they create this benchmark, which is essentially just a collection of a variety of different robotics tasks. And they train out all their policies using PPO. And yeah, this figure is a little bit small, but effectively you can see that MVP is their model. This one in orange is using Oracle ground truth state, and then yellow is Scratch supervised. And you can see that pre-training with the MVP features helps increase performance by a lot, getting pretty close to the Oracle policy, which has access to the ground truth states. So another potential issue that we have in robotics is that we have a large variety of different data that has that has many different modalities. Sometimes we might have only video data and we don't have actually the corresponding video trajectory or the actions that go with those. And so it'd be advantageous to like learn a representation that could leverage all these different data sets. So that's what we did in this paper at MTM. In MTM, we first take a bunch of trajectory data, and trajectories can just be thought of as a multimodal sequence of a variety of different elements. We might have states, we might have actions, we might have vision values. And so we flatten that into a common embedding space. And specifically, we just looked at simulated environments for this. We have states, rewards, and actions as our different modalities. And if we have missing modalities in our data set, then we can just treat that as like a forced mask. And then we can train similarly with the MAE type objective, where we randomly mask out parts in our sequence and then try to reconstruct those missing parts. So in this paper, we explore a variety of different things, but I'll only talk about the state representation one, which is the one relevant to this portion of the lecture. So the procedure is effectively we pre-train with some random masking using an MAE type of approach on these trajectory level data. And then downstream, we try to test how well these representations work. And that's what's being done here. So the setup is we have some offline data set of the robot doing a variety of different things. And we pre-train on these trajectories. We then run a RL algorithm on these learned representations and compare that to learning an RL algorithm on the raw states. And with these RL algorithms, sometimes you need the states, but sometimes you need like states and actions. And so we can also jointly embed the state action pairs using our feature extractor. So the green is the base feature extractor, orange is using fine-tuned, and then purple is using the state action features. And you can see that we're able to get better than the raw feature-based one, and sometimes even beat what the asymptotically trained state, or the asymptotically trained approach is able to get. So next, I'll talk about this work, mass world models for visual control. This is work led by Youngyo, done at his time in Berkeley. So the base of this approach is Dreamer. And we won't talk about Dreamer, but just so you all know what's going under the hood, there's two components. One is this world model, where you're trying to learn how your future states are affected by actions. And then the other is a policy learning aspect, where you use this world model to try to like learn a policy. The details, you can read the paper if you're interested in this type of direction. The innovation that Youngyo had here is that let's try to decouple the representation learning from the dynamics learning. So in this type of approach, we try to learn the representation as well as learn the dynamics of these representations. But potentially we can try to like decouple that and that might make things more efficient. So that's what's done here in this visual representation learning phase shown on the left. And then correspondingly, we will then do dynamics learning on these extracted features from our learned autoencoder. And the structure setup that we have is, another mass autoencoder style structure, where we will learn this feature representation through reconstructing of random masks. Specifically, they make a couple of, Youngyo makes a couple of changes here that are actually quite important. The first one is to pass the original image through some conv layers first. And we'll talk about why that's important. And then in the reconstruction space, we're also going to pass in a mask token for the reward because we want, and we're going to reconstruct the reward as well. Idea here being that hopefully our state maintains the information that lets us like predict the reward that was assigned to this state. This top part is this new representation learning loss. The bottom part is the original world model loss. Again, the math you can all look at if you're interested on your own. And so this is the corresponding results. The top sequence of images is the ground truth sequence of images. This one is the reconstructed version using masked world models. We have a predicted version, which is you effectively roll out in your world model space and try to see the corresponding images of what it will look like, and the bottom is predicted from Dreamer. And in this case, it's kind of hard to see, but there's this like little apple that the robot is trying to move. And you can see that the apple is present here in the robot with masked world models, but you see it's actually not present here in Dreamer. And what's happening is that Dreamer kind of is paying attention to these pixel level features that are more heavily present in the image, but kind of forgets about this to model this smaller, like less relevant feature of this apple. And it turns out that this reward prediction component and the convolutional feature component helps the model pay attention more to these features. The convolutional component kind of allows the features that you pass before into the MAE to have greater context. And so it's able to kind of, if you have a very small object like this this cube that you're trying to pay attention to, it can help allow the model to pay more attention to these smaller pixel-wise elements in your image. So yeah, masked world model is able to perform the base algorithm. You can see the blue curve is able to outperform these down here. And again, here is the ablation on using the conv feature. So if you remove the conv feature, if you remove the conv feature, you see that you're actually not able to do that well. Actually, Dreamer works better. But adding those few convolutional features before you pass it into the MAE reconstruction objective helps a lot. So Peter briefly mentioned this before, but now we'll do the masked multi-view MAE. And in this setting, and robotics is a setting where we oftentimes have to deal with multiple cameras that are looking. So in this case, we might have an egocentric camera of the robot looking at the object, as well as like a third-person camera. This was from, yeah, and this is like a robot hand that we have a bunch of different cameras that are looking over the hand. So with MAE, the nice part about the transformer is that we can deal with everything in raw token space, and then like the encoder decoder doesn't care what the tokens actually are. And so we can map now two images, both views, the wrist camera and the overhead view, into the token space and try to do reconstruction. Just like with the prior paper, it was very helpful to have convolutional features first before patchifying and passing into the encoder. And yeah, the main idea here is to reconstruct masked viewpoints to learn cross-view information. So hopefully now we can predict from, given let's say parts of the wrist view, we should be able to predict what the third-person camera view looks like. As you can see over here, we completely masked out this other view. And so hopefully that lets us learn maybe more robust representation, since the model should be able to learn features that can reconstruct from different views. And downstream, we can now apply this model a few different ways. One is we can use the encoder just to encode both views, but it might be that downstream we only have like a single view. And so we can train the model on just a single view version of that, a single view version of the environment. So here's the performance. If you use the multiple views, you can see that that's helpful. But maybe, but we trained it in this multi-view, so maybe like that multi-view pre-training is helping it in this multi-view setting. This other experiment is we only give it a single control view from the front, and we use our pre-trained encoder, and we can see that we're able to still outperform the other methods, actually get more than double than without. So let's see. So another potential issue that we have in robotics is that we have to put cameras attached to the robot. Sometimes people move your cameras and then your policy no longer works. So it would be very advantageous to train a really robust policy that can work across a large range of different viewpoints. And we can apply this multi-view MAE idea to this setting, where we can generate a bunch of different views and then use the same like multi-view master world model training approach. So step one is we do this representation with viewpoint randomization. Instead of having just the wrist camera and the overview camera, we're going to randomize these different viewpoints. And then we learn using our RL algorithm on the features from this learned encoder. And downstream, we can see how well this model is able to apply when we apply a bunch of randomizations to our camera views. And we're able to see that this multi-view approach is able to outperform prior approaches. And here's a real-world example of that, where now this robot, which is only taking in camera images, is robust to all these different augmentations of how we're actually holding the camera. So despite the fact that we're shaking the camera around a lot, or moving it around a lot, the policy is still robust to these changes. Cool. So I think I will end lecture here. We have some small components that I left in the slides with regards to language models, but we're going to have a language model dedicated lecture next week, so I think it's okay if we don't fully cover these. So yeah, thanks.